Hello and welcome to the presentation on the text polarity classification assignment for data science and machine learning. My name is Pohan Ho and my student ID is 109607515. If you have any questions regarding the content of this presentation, please feel free to contact me using the email provided below. Here's the overview and background of an article discussing different algorithms used for product feedback classification on popular websites such as Yelp, Quora, and Amazon. The training dataset for this research included 2,000 product reviews with an additional 500 manually labeled test datasets reviews added to the training datasets. I applied text preprocessing by removing punctuation and exclamation signs. Text vectorization was performed using an embedding dimensions of 128. 8 algorithms were used in this research. This includes TF-IDF plus multinomial naive Bayes, and vanilla DNN, LSTM, GRU, and so on. These algorithms were tested and compared for their performance in classifying product feedbacks. About my experiment design, I concluded that there were 4 methods to transform the dataset. The original dataset was 50% positive and 50% negative reviews. The second method involved adding augmentation to the original dataset, resulting in a split of 50.16% positive and 49.84% negative reviews. Text preprocessing was applied as the third method to the original dataset, while the fourth method involved applying both augmentation and text preprocessing to the original dataset. The applied methods of algorithm are as below. The first algorithm was a baseline, which used TF-IDF and naive Bayes to classify the text. The second algorithm was the simple DNN, followed by LSTM, GRU, bidirectional LSTM, bidirectional GRU, and 1D ConvNet. Finally, the 8th algorithms were used pre-trained universal sentence encoding and DNN. This page shows my functional flow block diagram, which illustrates the flow of our experiment. As you can see, we have the original dataset and augmented dataset, and we compare the performance of applying text preprocessing on these datasets across 8 different algorithms. We aim to identify which combination of data transformation methods and algorithms produce the best results in terms of text polarity classification. This page shows an example of our natural language processing work. As you can see in the image on the left, it displays a sentence from the original dataset. In the middle image, we remove the punctuation marks from the sentence in the image on the right. We further remove the stop words from the sentence. This process reveals some potential issues that are highlighted with the red lines. Regarding word vectorization and word embeddings, I used word-level tokenization, which is a way to assign an index to each individual word based on its order. For the embedding size, I followed the literature of transformer and BERT model, which typically use a size of 128. The table below shows the average sentence length for the 4 datasets. The universal sentence encoder is a natural language processing technique that converts sentences into vector representations. This allows for easier processing of large amount of text dataset. The USE includes 2 models, the transformer encoder based on the transformer architecture, and a deep learning based DAN model. These models support multiple languages and are suitable for applications such as text similarity comparison, sentiment analysis, and question answering system. One of the benefits of the USE encoder is that it can be loaded through TensorFlow Hub and fine-tuned in TensorFlow for improved performance. This allows for greater flexibility and customization in the implementation of the model. Finally, it's worth noting that the USE has demonstrated excellent results in various natural language processing tasks, making it a powerful tool for any NLP projects. Let's talk about the Lab 1, which dealing with the original dataset. The table of the Lab 1 compares the performance of different models on 4 indicators. The USE plus DNN models performs the best with an accuracy of 80% and F1 scores of 0.799. Utilizing pre-trained USE embedding in contrast, using In contrast, the 1D ConvNet model performs the work with an accuracy of 66% and F1 scores of 0.659, likely due to 1D convolutional layers not being ideal for the text and not having enough parameters to learn patterns effectively. Lab 2, the dataset now has content original 1 and the augmentation. Comparing the results in Lab 1, it is clear that the overall accuracy has decreased, especially for bidirectional LSTM, which dropped from 71.5% to 64.4%. And since almost every algorithm's performance was affected, I personally attribute the decline to the augmentation. When examining the original data tested, we knew that it was difficult to determine whether a review was positive or negative, and now we have learned that the human labeling annotations may have been the reasons for the failure in Lab 2. Lab 3 is the most common way to undertake the NLP task. In Lab 3, we faced the similar issues as in Lab 2, where the overall performance dropped. However, unlike Lab 2, the best performing algorithm, US plus DNN, did not suffer a significant drop in performance and was still able to perform well in polarity classifications. On the other hand, the 1D ConvNet algorithm showed the worst result among all the tested data algorithms. In addition, I observed a phenomenon where the LSTM and GRU-based model have the same accuracy, which further leads me to believe that it is not a problem with the algorithms but rather with the data. Finally, we put the transform methods all together at Lab 4. It is not surprising that after encountering the problems in Lab 2 and Lab 3, we cannot expect the results to improve. In fact, the two confounding variables affected the results simultaneously, resulting in worst-case scenario of all experiments conducted. The accuracy of LSTM almost dropped to under 60%, and the USE plus DNN dropped by about 10% in this case. However, after conducting these 4 experiments, I am confident to say that the USE plus DNN is the best model in our current evaluation. Let's compare Lab 1 and Lab 3 as they differ only in whether or not they perform text preprocessing. The red text below indicates the accuracy of the best performing model, which are 80% and 76% respectively. It can also be observed that performing text preprocessing seems to have increased the precision of the LSTM-based network. Let's compare Lab 2 and Lab 4 and investigate the effect of data augmentation on text preprocessing. However, based on the results of Lab 2 and Lab 3, we should not expect the performance to improve with both data augmentation and text preprocessing. And moreover, when comparing Lab 1, 2, and 3, it can actually be seen that the impact of augmentation on the model is greater than that of text preprocessing. During the discussion, it was found that increasing the amount of preprocessing such as augmentation and text preprocessing results in a decrease in model accuracy. Augmentation was observed to have a greater impact than text preprocessing with a decrease in accuracy from 80% to 73.6%. The performance of famous recurrent neural network architecture was found to be mediocre in this dataset, but bidirectional training showed a slight improvement. Manila feed-forward neural network performed well in all datasets, while 1D ConvNet performed the worst. The use of a pre-trained USE layer demonstrates the best performance in this experiment. Now, let's move on the possible solution to improve the model performance. Firstly, we can try to generate augmented data via GAN or VAE as we learned in the class. These methods may improve the model's ability to generalize and achieve better accuracy. Another approach is to use other pre-trained structures such as transformer, BERT, or glove embedding layers. These models have been trained with abundant data and might be able to help us to achieve a higher score than our current model. Lastly, we can also try combining USE with LSTM or GRU to see if we can further improve the accuracy of our model in this dataset. Today, we work on a project that involve text polarity classification or product reviews. We explore various techniques such as removing punctuation, exclamation marks, sample removals, and human determination to create training dataset. Interestingly, the results show that using the original dataset without any preprocessing or augmentation performed the best. We found that pre-trained embedding layers, particularly in combination with a simple DNN, outperform other algorithms. However, popular algorithms such as LSTM and GRU did not consistently surpass the baseline. Finally, we concluded that utilizing a high-quality pre-trained embedding method such as USE, Glove, or BERT can be the key to achieving the best result. Here's references and related work with respect to the assignment, sorted in alphabet order. This is the end of my assignment reports. If you'd like to hear more information from me, please subscribe my channel. Thank you.